Good afternoon and welcome to Offshore Wind North East Conference. My name is Gareth Ellery. I'm one of the directors at Cathies Group. We provide expertise seabed and below, and we are the global offshore geoscience and geotechnical engineering consultancy. I'm really pleased to be here today to present to you on some geoscience and geotechnical considerations in the floating offshore wind sector. And what we're really going to do here is kind of compare and contrast our experience in the floating wind sector with fixed bottom offshore wind and really bring that to life, hopefully, for you as the audience. So let's get started. Cathie have been involved in floating offshore wind since 2011. It's really part of our portfolio of 75 gigawatts of offshore wind experience globally. We got involved in floating offshore wind organically, really. It was just an evolution of our involvement in conventional offshore wind, and it fitted really well with our historic involvement in deep water oil and gas and floating facilities and platforms in that sector. We're involved throughout the project lifecycle, from really early stage site selection through into design of cable routes and cable burial, subsea foundation systems, all manner of things really. Initially, back in 2011, we were engaged with device developers, substructure floater developers, but now increasingly we're getting more involved with project developers as floating wind commercializes, and we're seeing a real shift towards project development. We are currently involved with developers identifying suitable lease areas for floating wind in Scotland and in England, Wales, round 4, looking more globally as well for suitable areas. It's pretty clear to us that floating wind is essential in global markets if we're to realise the scale of offshore wind overall. So what have we learned? And here really I'm comparing floating wind to the relatively established technology of offshore wind. Starting off with subsea cables. The cables are dynamic, which presents challenges in and of itself. Some projects require the touchdown point to be examined in detail, looking at that cable soil interaction, that system, modelling the cyclic loads and the potential fatigue on the cable. We see in deeper water there's a lower risk to infield cables. The export cables, same level of risk in the shore approach, but as we go offshore towards deeper water, much less risk to the cable as well. So there's a clear difference between floating wind and fixed bottom wind there. And that leads really to the potential for infield cables to be surface laid, depending on the on-bottom stability at the particular site and the inability for fishing trawlers to access the development area. We would expect that to be a case anyway because of the mooring lines and the water column. In subsea cables, ideally, we really need wet mate connections, which is a big difference from fixed wind, and that's to enable the substructure to be towed back to port for OWNE. The water depths on these sites are typically prohibitive for jack-up vessels to undertake gearbox or blade changeouts, for example. There is the potential, we think, for using some innovative new concepts like cable in pipe, which we're working on with the Carbon Trust, which reduces the dynamic behaviour of the cable and also reduces the cost. If the substation's floating, there will be a transition required on the export cable from dynamic behaviour to static as well. We foresee that can really be engineered in onshore, as opposed to having this kind of joint or transition made in the offshore environment, which increases risk, cost and time. On the foundation design side, we are seeing a focus on lighter, lower intervention, mass production foundation systems. The water depth on these sites really forces subsea operations from floating vessels as opposed to jackups for fixed bottom wind, and we tend to be looking at less resilient foundation types. The interventions available to us subsea from floating vessels are a lot less than we might see from a fixed jack-up platform. The consequence of failure is higher. If a foundation system fails, just a single foundation system, then that can overload the remaining mooring lines and foundation systems and cause a significant loss of position of the substructure, potential collision there with adjacent floaters. So that needs to be borne in mind when we're looking at the design of subsea foundation systems. The project economics tend to be encouraging foundation anchor sharing, where we see a single anchor point and multiple mooring lines from adjacent foundations. That does have some disadvantage in that the mooring lines are extending a long way laterally through the water column. So we really need to see how that works out at commercial scale. Deeper water sites are tending towards TLP and sway concepts in an attempt to reduce the mooring footprint. So we really have this interplay between different mooring types and the ability to share mooring locations to cut costs. There's offsets to be had between these different approaches. Using floating wind reduces seismic load to the substructure, and that is obviously a very good thing. But shallow foundations are potentially more susceptible to liquefaction and seabed movement. We need accurate load time series data for the mooring lines attaching to the foundation to be able to design them properly, particularly where single foundation points are being used for multiple mooring lines. And finally, the environmental and fauna implications of mooring lines throughout large project areas is in the water column still being understood. The project development stage, we still think there's currently a lack of investment in seabed risk management and project development. There is, or has been in the past, a tolerance of high seabed risk due to the focus being on the wind turbine generator or floater development. That is changing. On the survey side, we see a focus on shallower depth because of shallower penetration of foundation systems, but a requirement for higher resolution due to the sensitive nature of the foundations we're attempting to use, like suction caissons, and the reduced intervention potential during installation. Across these footprints, there's a much larger potential geotechnical and geological variability over a single wind turbine because of the mooring area. That needs to be considered as well, and that implies that we need more detailed survey data over a wider footprint within the project area. There is a great potential to decouple the foundation and cable installation from the wind turbine and substructure in the project programme. Again, wet mate connectors for the cables really enable this potential advantage in the project, which is really significant. And finally, we do need to bear in mind the potential impact of mooring pattern on optimal wind turbine spacing in deeper water. We really don't want the mooring pattern pushing the turbines further apart than is economically the best solution. Thank you.